Hey everyone, Mr. Cummings here, and in this video we're going to take a look at deriving a shortcut for the elastic collision problems. So we're going to start this derivation with two main points, and that is going to be that in an elastic collision, momentum is going to be conserved and total kinetic energy of the system is going to be conserved. So we're going to assume in this derivation that we have two objects that are going to be colliding, object A and object B, where the mass of object A will be ma, mass of object B will be mb, and then the velocities will be va and vb respectively, but we'll have initial and final velocities since we're looking at the total momentum, the total kinetic energy before and after a collision. So we'll expand both of these equations into a longer form where we have the initial and final momentum is equal to the initial and final momentum of each object added together, and then the same thing for kinetic energy. So now that we have both of our equations written out, we can go ahead and cancel out the 1/2 in all of the energy terms, since there's a 1/2 in every single term in that equation. So now we're going to take a look at the conservation of momentum equation on the left, and we're going to manipulate this. So instead of having the equation broken down into initials on the left side, finals on the right side, we're actually going to group object A on the left side and object B on the right side. And we're going to do that just by subtracting each term to move it to the other side. Now that we have the equation grouped so that all of object A is on the left side, all of object B is on the right side, we can see that we have a common term or a common variable in each term on the left-hand side, which is ma. So we're going to factor out an ma, and then we see the same thing on the right side. So we're going to factor out an mb on the right side. What that's going to leave us with is ma multiplied by the difference between the initial and final velocity of object A. And on the right-hand side, it's going to be mb multiplied by the difference between the final and the initial velocity for object B. Now the last thing we're going to do to this equation in this derivation is we're going to isolate the term ma. And we're going to do this because this will give us something that we can then substitute into our other equation. So we'll effectively be able to eliminate a mass term in the kinetic energy equation on the right-hand side. So we'll do this just by dividing the parentheses statement va initial minus va final by both sides, and that's going to give us an expression for ma. Now we're going to go ahead, we already canceled out the 1/2, but we're going to write the equation without the 1/2 just to clean it up a little bit. And now we're going to do something very similar to what we did in the momentum side. So instead of grouping this kinetic energy conservation equation by final and initial, we want to group them by the object. So we want all the MAs, or all the terms that are dealing with object A on the left-hand side, all of the terms dealing with object B on the right-hand side. So again, we're just going to subtract each term from each side, moving it over to the other. So doing this leaves us with an equation where we have something very similar going on to the momentum equation again, where we can factor out an ma from the left-hand side, and we can factor out an mb from the right-hand side. So what we get is an expression where we have ma and mb both multiplied by the difference of two squares. So if we look at this as x squared minus y squared, we could factor that into x minus y multiplied by x plus y. So we can apply the same concept to va initial minus va final, and so what we get on the left-hand side is mass of A multiplied by the parentheses statement va initial minus va final multiplied by a new parentheses statement, which is va initial plus va final. And the right-hand side, we'll get something very similar, just with vbf and vb initial instead of va. And so now what we see here is that we have this expression for ma from the conservation of momentum, and we have an ma term on our conservation of kinetic energy equation. So we're going to substitute in this equation for ma into our current equation. And when we do that, we're going to be able to cancel a bunch of different things out, and we'll show that in our next step. And so I used square brackets to show what the ma term was, which is now mb multiplied by the ratio of these two parentheses statements. But plugging this in, all we've done is we've replaced ma with the equation from conservation of momentum, and we get this new expression. So we get to cancel out mb on both sides, and then we see that we have va initial minus va final in the denominator and the numerator, so we cancel those out on the left-hand side. And then we have VB final minus VB initial on both sides, so we can cancel that out as well. So after doing all of this algebra and keeping track of all these terms, and then finally canceling everything out, we're left with a very elegant solution to this problem of an elastic collision between two objects, and that is that the sum of the initial and final velocity for each object should be equal to each other. So we can use this whenever we're analyzing problems that are perfectly elastic.